Hey guys, in a previous video we talked about the basic definition of porosity and what types of pores constitute what types of porosity. And I mentioned that we can have, since porosity is a void fraction, that it must range from 0 to 1. Now, I want to talk about, in this video, I want to talk about how we can derive a value for the maximum porosity. Now you might be thinking, well, if it varies from 0 to 1, then isn't 1 the maximum porosity? Well, in a sense, you're right. But physically speaking, if we actually do have a physical medium, such as a rock with grains, with pore spaces in between, it is not possible to have a porosity of 1, because that would mean that the pore volume is exactly the same as the bulk volume, which would mean that we don't have any rock grains at all. So that would just be describing, I don't know, air or some vacuum. So today in this video, let's talk about, given the physical constraints and limitations that we are put in this world, that exist in this world, what is the maximum porosity that can be derived? So for us to be able to derive this value, which as you can see from here is 47.64%, we will go study a little bit, we'll take a little bit of techniques from material science, where there is a subcategory in this field of sciences called crystallology. Well, I'm not sure how to spell that, but we'll just call this as crystal structure. So crystal structure is referring to, is like a description of the grains or molecules within a crystalline material. So this is actually, as it turns out, perfect for petroleum engineering because we can use these techniques to describe some of our rocks which have porosity. Let me finish quickly writing that. Crystalline material. Okay, so we're going to have to put some limits on ourselves because remember, our objective is to find the maximum porosity, which is equivalent to the least dense packing within a material. So we're going to have to do a little bit of head scratching. We're going to have to do a little bit of thinking. So what are some possibilities that we need to look at for us to be able to derive a maximum value for porosity? Well, we're going to have to find a way to define volumes, be they pore volumes or grain volumes, in a structure. We are going to need a way to define packing, which coincidentally would also give us the definition of porosity in such a structure. I'm just going to put speech marks there. And we are also going to have to put some constraints on our structure to make it easy for analysis. Now, a lot of smart people have done a lot of thinking about this, so we won't go too much in depth on that. But I will just tell you that the shape that we will be choosing is a cube. So now a natural question might be, oh well, why a cube? Well, a cube is simple enough for us to analyze. That's number one. It's simple. But more importantly, a cube is a unit that can be tessellated, which means that it can be stacked repeatedly in all directions. So given that it can tessellate, it means that it can be stacked repeatedly in all directions. So it is therefore a useful unit cell for us to start our analysis. So now that we have chosen a simple cube shape as our starting reference point, we need to think about what can fit inside a cube. So let's take a deeper look. Let's say that we had grains of a rock. Now, it might not be obvious to you, or it might be obvious to you, that rock grains can be of varying sizes. We could have a really large grain here, surrounded by some smaller grains, surrounded by ever smaller grains. So if we use our imagination, we will find that having this kind of arrangement actually limits our ability to have a maximum porosity. For the simple reason that, let's say that we had two of these large grains nearby each other in such a way, so we would have, we would have qualitatively speaking, we have some large pore spaces, but then these would be filled by smaller grains, like this. And after this, we still do have some pore spaces, but then those will be filled by our ever smaller grains. So it seems that having different grain sizes is a no-no. So no different grain sizes. Okay, well, let's try something else. What if we decided to take everything to be the same grain size? Well, then we might have something like this. So that seems reasonable. This seems to have more pore spaces, just qualitatively speaking, compared to this one. So it seems like this one is a better choice. So from here, we know that grain size affects porosity. So what affects our porosity? So one of them is the grain size, which we have just shown simply. Also the way that they are packed. Let's say that I pack some cubes in this way. So I would have some space like this, but what if I decided to pack them in this way instead? So notice how here we have the centers lining up vertically and horizontally, like so. But here we have them lining up diagonally. So the angle that this forms over here varies. Okay, so this would have different packing effects. Just qualitatively speaking, this seems like it has even less porosity. Okay, well, we know from research and literature, we know that this is also affected by other things, such as the shape of the grains. It is also affected by the sorting, which is referring to the grain size, and various other factors. Because shape can be split further to angularity and roundness, as well as the length compared to its width. Okay, so now I want you to convince yourself that in order for us to have the maximum porosity, which would mean that we need a least dense packing, that we would need what is known as a cubic packing. So there are lots of ways to pack grains into this cube, but I want you to convince yourself that there is no possibility for us to find some other arrangement that would allow us to have a higher porosity than this, because as it turns out, this is the shape, or this is the packing that leads to the maximum porosity. There's no other shape that leads to this. And the way that this works is we need to imagine that in each corner of this cube is an eighth of a circle. So an eighth of a sphere, my bad. Alright? So in the middle we don't have anything, but we don't have a single sphere in the middle, but we do have 8, 1/8 of 1 over 8 of the sphere's volume. This is because we're only taking it from one octant, yeah, on each corner. And we have 1, 2, 3, 4, 5, 6, 7, 8 corners. So now I want to define a variable or a parameter in the study of crystal structures known as APF, which is the atomic packing factor. This is a measurement of how densely packed a unit cell is. So the higher the APF, so a higher APF leads to a more dense packing. As it turns out, 1 subtracted by the APF actually gives us the porosity. Alright, so what is APF? So the APF, since it is a factor that determines our atomic packing, or how densely packed a unit cell is, as you might imagine, since it has something to do with volumes, this is the volume of the unit cell in the denominator, which is the bulk volume, and at the top here we will have our grain volume. So the grain volume is given by the number of particles within the unit cell multiplied by the volume of a single particle. Alright, so let's go back to our cube. Alright, so now let's talk about the atomic packing factor that we can expect from a simple cubic arrangement. So here we draw a cubic unit cell, fill it up with some octants, or 1/8 of a sphere. Now it's a little bit hard to draw this. Don't be too pressured to draw something beautiful because everybody knows that this is quite the struggle. Just try to remember to draw a 4-pointed star in on each face, and try to add a bit more lines to give it some character, to show that indeed this is representing 1/8 of a sphere. Easier said than done, but if with enough practice and hopefully with better drawing skills than mine, you'll be able to do that easily. So now we know that these spheres start from each corner. The centers of each sphere coincide with the corners. So maybe I should use yellow for this so it's a bit clearer. We also know they end exactly halfway. So these facts allow us to make some deductions. We know that this distance must be r, and so must this distance, because this is exactly half of the square. So the distance of the side of this cube is actually 2r. So now using the definition of our atomic packing factor, well, we know that the number of particles is just 1/8, because there's 1/8 of a sphere multiplied by 8, so that gives us 1. The volume of the particle is given by 4/3 pi r cubed, and we'll just leave it as r for now. And the volume of the unit cell is given by, sorry, that should be a 2. It will give 8 eventually, but let's not skip steps. That will be 2r all cubed. So putting this in the formula for APF for a cubic packing, what do we get? So we get 1/8 times 1 for our number of particles. We get 4/3 pi r cubed as our volume of a single sphere or atom or grain, and we get 8r cubed down in the denominator for the volume of the unit cell. My bad, there should be an 8. So these cancel to give out a 1. What we're left with is 4/3 all over 8 pi. These r cubes cancel. So this gives us 4/24 pi, which is ultimately pi over 6. Now, if we recall, the definition of porosity is 1 minus the APF. So we have derived the porosity, the maximum porosity, which is just 1 minus pi over 6, which if you punch in the calculator should give you 47.64%. Isn't that wonderful? So you can also use this technique to find the porosity or atomic packing factors and the porosity of different arrangements. So unless you try it yourself, it is not that easy to convince you that this is indeed the least dense packing that we can get for the case when we have a unit cell that is a cube, also with evenly sized grains. But I guarantee you, if you try it, you'll be able to see it right away. So, if you ever need to calculate or need to find out what the maximum value of porosity is, well, you have two options. One, just memorize it, or two, quickly do 1 minus pi over 6, where pi over 6 is the atomic packing factor of a simple cubic packing unit cell. Alright, so this was how to derive the value of maximum porosity in petroleum engineering. So I hope you like the video. Leave a comment and subscribe. Also click the bell icon for notifications. Thank you for watching and stay tuned for more. Bye.